for help. Thermal physics. Thermal physics. Mr. Ryan, that's very late. Hmm? How are you, Mr. Ryan? Mr. Ryan, can you hear us? Ryan, can you hear us?
Hello.
Can you hear us?
Yes, I can hear you.
So I'm saying that's very late. For these lessons, for my lessons, people should be very punctual, even wait for the
Don't have
teachers.
weekend.
Okay. So now let's term of physics. Let's start with heat. This is a general topic, but it has some calculations. Huh? So what do you understand by heat? What are we talking about when we talk of heat? We can define heat. What do you think is heat? Heat is simply the transfer of energy from a hot object to a what? To a cold object. Huh? It's the transfer of energy, heat. Transfer of energy from a hot object to a cold object. It's always like that. It's never the other way. Clear? The transfer of energy from a hot object to a cold object. Making sense?
Yes, sir.
Okay. Now, my first question, before we even go further, is what if I have two substances that are made of different matter? With substance A, substance B. They have this, so these are two different substances, but they have same mass. Same mass. Okay, mass, let's say both of them equal mass. Then we expose both of them to the same amount of heat. What do you think will happen? Same amount of heat. Huh? You don't have to draw that. We just what will happen if we expose them to the same amount of heat? What observations? What can you or what conclusions can you make? Same mass, same amount of heat, but they are made of different materials. Huh? Different method means one can be a solid or they can have different, you see, they can have same mass, different densities, that's what I mean, or same mass, maybe even different arrangement of, like, it can be a liquid and the other one can be, but it's same mass, the other one can be a solid. So what will happen? Both of them, the temperature or what? We are, remember, we are exposing them to heat, same amount of heat. Both of them, in general, the temperature will increase. Are we agreeing? Both of them will increase. But will the temperature increase at the same amount? No. It's dependent on the type of what? On the type of substance. Is that clear? It's dependent on the type of substance. So if this was a solid here, to bring it closer to home, and this was water, which one do you expect temperature to rise quickly? We are same amount of heat with the solid and the liquid. Which one would you expect?
The water.
The water would rise temperature quickly. Do you
Yeah.
agree with him? The water or the liquid? Do you agree with him that the liquid, which is a good conductor of heat, liquid or solid in general? Water or a liquid is a poor conductor of what? Of heat. Remember particles. How does heat travel? Look at this. Heat is traveling, okay, by convection currents or by conduction. The particles are further apart. The particles in a solid are close together. So a solid is a good, in general, is a good conductor of heat than a liquid. You see that? A liquid, water, especially the water that they have actually given, is a poor conductor of heat. Clear? So it means the liquid, the temperature will rise what? Will rise faster. Is that making sense? Okay. Clear? Which brings us to the main thing that we want to look at today, which is known as the specific heat capacity. We will explain it just now. Specific heat capacity is the amount of energy. Is the amount of energy. You can write those definitions down. Amount of energy required to raise temperature, of 1 kg of a substance. Temperature of 1 kg of a substance by 1 degree Celsius. Clear? By 1 degree Celsius. Is that making sense or not making sense so far? You guys are quiet. Making sense or not making sense?
It's making sense.
The definition, you need to remember the definition. The amount of energy required to raise the temperature of 1 kg of a substance by 1 degree. Okay. Then I'll tell you something. You don't need to remember this. Specific heat capacity, they always give you in the exams. Specific heat capacity of water is 4,200 joules per kg degree Celsius. So what it means is that to raise temperature, if I'm going back to the definition, it means to raise 1 kg, to raise temperature of 1 kg of water just by 1 degree Celsius. How much energy do I need? 4,200 joules. Clear? That's what I need to raise the temperature, clear, of water. That's a lot altogether. So you find that copper, like what we said, copper won't need so much energy. Copper, I think the specific capacity is about 830. Some books say 700 something, clear, around 830. That's the specific heat capacity of copper. Because copper is what? Is a good conductor of what? Of heat, yeah? So you require less energy to raise the temperature by 1 degree than water, which is a poor conductor. Clear? So if I'm given two materials, one has got a high specific heat capacity and the other one is a low specific, it means the one with a high specific heat capacity is a poor conductor, because I need lots of energy to raise the temperature by just 1 degree, to raise the standard 1 kg of that substance by 1 degree. Clear? Copper, I simply need 830 joules of energy altogether to raise 1 kg of copper, raise the temperature by 1 degree. Chair, does that making sense? On specific heat capacity.
It's making sense.
Okay. Okay. Now, before we look at the formulas, the main thing for the day, let's look at certain things here so that we add up. So in physics, you have a heating curve. I'm sure I have done that even at maybe at lower Cambridge. Then we've got what is called a cooling curve. Clear, you can sketch them there. So this is for any substance in general. I'm sure you know this. It's something like this. Yes? Question?
My explanation will code the lesson.
Oh, sorry. I thought I was recording. No, I'm recording. You want to record? Oh, it's Takuzo. That Takuzo? That's Takuzo? Because I know he's Takuzo always asking me to record. You are not recording. So this is what we call a heating curve. We'll explain certain things that we need to know everyone there. So I can write A, B, C, D, E. Follow me? F here. Let's do the cooling curve, which is the opposite. Of course, not straight. Like this. So A, B, C, D, E, F. Clear. Now, A, so this is temperature, which is increasing, and this is your time here. Temperature and time. Clear. Follow me. A being the substance it's a solid, that is, you are heating up a solid. Clear. So it's a solid. So at that stage, it's solid state. The object is in solid state. It applies for any substance. Solid state. BC is what I want to explain more. BC is the solid is what? Melting. Clear? Solid is melting. If you want, it's actually the melting point. Why is the temperature constant? Who knows that? Melting point. Why is the temperature constant on BC? Why is the temperature not heating? No, not rising. We were heating a solid, then all of a sudden when it reaches the melting point, the temperature is constant for a short time. Why is the temperature constant? Who remembers? Chiesa, why is the temperature constant? Why is the temperature constant? What's the reason? Mufaro, what do you think? You've never heard about it? Or you've forgotten? Takuzwa, quiet. Natalie, so no one can pick this. The temperature is constant. Why is the temperature not changing? Because, why? This is a solid, and this solid is now turning to a liquid. Because at melting point, you can write the reason. At melting point, the temperature, the heat energy is used, right? And I don't have space here. The heat energy is used to overcome the forces of attraction. The heat energy is used to overcome the forces of attraction, holding the solid particles together. The heat energy is used to overcome the forces of attraction, holding the solid together so that it can change to a liquid. Clear? So as opposed to increasing the temperature, the heat energy is being absorbed by the solid so that it overcomes the forces of attraction, holding the solid particles together so that there can be a change of state. Clear? Is that clear? Or while someone needs further explanation? Because there it's a solid, particles are further. When these particles, they've got a force of attraction for every solid, that depending on the material. They are closely packed. So for it to move like this so that you have spaces, it becomes a liquid. You need to overcome the forces of attraction. So we're saying at melting point, that energy now is not being used to raise the temperature, is being absorbed by the solid so that it overcomes all the forces of attraction holding the solid particles together so that it can turn to a what? To a liquid. And that's why temperature remains constant for a certain amount of time. Clear? Making sense? Constant until it becomes a liquid. Huh? Making sense now? That making sense?
Sir,
Yes.
Yes?
I'm having some trouble understanding.
Okay, where exactly?
So, okay.
Your question is yes. Do
So
you
I'm not gonna lie. I like the whole concept is just
do you know
bothering.
okay, look at this. Don't complicate life. What do you know about a solid? A solid particles are what?
They are very tightly packed.
They are tightly packed. Tightly packed. So I am saying there it's a solid. Until I reach this point, that's where the melting is. Now I'm now explaining the melting. So we are saying now, listen to the concept now. Because for these two, they are tightly packed. A liquid is what? The particles are a bit further apart. Huh? So for this to happen, there are forces. There are forces that are holding these solid particles together. Those forces have to be broken down. And it needs a very large amount of energy. Clear? So the
Yeah, very
energy
clear.
now, and that's now why the temperature is not increasing, because all that energy is being absorbed. So that the particles can now, so that we can break the force of attraction between the solid particles. So that it becomes a what? A liquid. Do you now get the concept?
Yeah, I do. So the point is to break up the solid particles and turn them into liquid particles.
Yes, to break the
Oh, I
forces of attraction.
All
Not
right.
really the
Thank
particles
you.
themselves. The particles are not breaking. We are breaking the forces of attraction holding the particles together. And that energy, you can write that energy is called the latent heat of fusion. Clear? In brackets, the energy is called the latent. That total amount of energy that we require is called the latent heat of fusion. Latent heat of fusion. Making sense now? Latent heat of fusion. Takudzwa, you're quiet. Yeah, then.
Energy bringing in and also I can understand. So
Your network is breaking off,
yeah,
but I'm recording, yeah? So get it, maybe you
you
get it.
will you send it to me?
Yes. Stay in the lesson if you can hear something. I'm not sure what's happening with the network. Also, you're the one who was being logged off there. Then look at this there, chairs and friends. So at this point here, it's now totally a liquid. Huh? Clear. Then the temperature, as you heat the liquid, the temperature continue rising. Then at this point here, the same thing that we explained here is now boiling point. So why is the temperature constant? Remember, we want to change from a liquid to what? To a gas. So even if the liquid particles they look like this, there are actually forces of attraction in a liquid clear between particles of a liquid. So these forces of attraction, now when we want to move to gas, these forces of attraction have to be broken down. So it's the energy is being absorbed. That's why the temperature is constant, so that the liquid can change to what? To a gas. Then at this point here is now completely a gas. Clear now, everyone? We are heating. Cooling curve, we are decreasing the temperature. So it means there is a gas. There, when something changes from gas to liquid, what do we call that? What is this point known? Gas to liquid? You guys are quiet. Gas to liquid.
Is that not condensation?
Condensation. Point. Clear? Then there, this is a solid. So solid to liquid, freezing. Huh? Freezing point here. The same concept. Clear? Clear, clear, clear. Okay. Now let's now go and look at the special formula. E is equal to mc delta T. I'll explain everything. E is the energy. E is the energy. M is the mass in kgs of a substance. C is the specific heat capacity. Then delta T is the temperature change. Are we together? Delta T is the temperature change. Cheers, are you there? You're very quiet. Are you there? Oh, you are lost. I hope you are in the lesson. I can see you there. Cheers, you are there? So this question has got a few calculations. The rest is theory. We look at the radiation, all that, the things that you look at for. Then we add something from your form 2, form 3. Day clear. The rest is easier. Now it's just the calculation that I want to study so that we master them. Now let's write the following example. Then it will make sense just now. Write question 1. Question 1. Question 1. Write in your notes. Is that Chakos or that we are losing again? Question 1. I think so. So how much energy? How much energy? Here's are you still in the lesson? We've gone for supper. Can you hear me? How much energy will it take to raise 3 kgs of water by 5 degrees Celsius? Then they always give you specific heat capacity. According to the question, specific heat capacity of water is equal to 4,200 joules per kg per degree. Joules per kg per degree. Joules kg degree. Degree Celsius. 4,000 like this. Joules per kg degree Celsius. That's what I mean. Specific. Let's use our formula. Chieza, are you there? Chieza, can you hear me? Yeah, very quiet. Chieza, can you hear me? Cristiano, this is very, very late. Huh? What's happening with you?
So I was doing homework.
Oh, you're supposed to, because now you'll be lost now. You're supposed to be very early for this lesson. Now, how much energy will it take to raise 3 kgs of water by what? Chieza, is your mic working? You're very quiet. Chieza? She muted or something. Mufaro, can you hear me?
Yes, I can hear you.
Natalie, you can hear me?
Yes, sir.
Okay. So what's happening with Chieza? Maybe she muted. Now let's look at this. So E We said E is equal to energy is equal to mass times specific heat capacity times the temperature change. What is the mass? 3 kgs. We said mass in kgs.
3 kg.
Multiplied by what is the specific heat capacity? 4,200.
4,200.
What is the temperature change? We are told to raise by 5. So that's the temperature change. There. And use your answer. What's your answer there? Use your calculator. Energy in joules.
$63,000.
Yeah, 63,000 joules or 63 kilojoules. So 63,000 joules or 63 kilojoules. Clear? Solution there. Hope you are writing that solution in your book there. Cheers, are you there? You see in the lesson. Can see here, but I can't hear you. Clear, clear, clear. Let's look at another question. Question 2. It's good to do questions in your notebooks or wherever you write important notes. Question 2. Now a block of, so this one I want you to try. I'll give you 2 minutes. A 5 kg block of copper, a 5 kg block of copper in brackets, specific heat capacity. That means that copper specific heat capacity is equal to 385 joules per kg degree Celsius at 20 degrees is given 46,200 joules of energy. What will be the final temperature? So can you calculate that? 2 minutes.
Simple.
Yeah, done. I think simple. Chedza there in the lesson. Is she gone for supper? Are you guys done?
Yes, sir.
You saw that it's simple. It's not difficult. Everyone done so that we can revise? Takudzwa, done? Takudzwa, you done? Okay. I think it's network. Okay, let's revise. Quickly. Mufaro, you're done. Mufaro? Yeah, done.
Almost.
Huh? Mufaro, it doesn't take time. Yeah. It means there's something that you might be doing wrong. Because it's simply a matter of rearranging and getting things. Changing subject of the formula and getting correct stuff. So look at this here. I'm not sure what your answers are. So look at this, everyone. What's your answer? Natalie, you said you're very fast. You're the one who said simple. What's your final answer? What's the final? Who can tell me what?
24.
24.
I got 24.
Okay.
Not so
Not
sure.
really correct, huh? Is that Natalie? I'll tell you why it's not
Yes,
wrong.
sir.
Why it's wrong there. Kiedza, what did you guess? Quiet. Mufaro, what is your answer? If you got this, it's not correct. I'll show you why.
Was I supposed to subtract the temperatures?
No. Why should you subtract? When you are applying heat, it's the temperature is going to increase. Huh? The final temperature. Clear? You are applying this amount of energy, the temperature is going to increase. Clear? T in the formula here is temperature change. Yeah. It's not just the temperature, it's the temperature change. So the answer that you got here is the temperature change, not the final temperature. So you're supposed to add this to the initial what? You see, you're almost there to the initial temperature.
Temperatures.
Because this is simply temperature change. Okay, so let's do that together. E, yes, maybe you joined late. E is equal to M delta T. Follow me. It will make sense just now. So what I need is to make this the subject of the formula from physics. So to make the subject of the formula, I simply divide both sides by MC. This by MC, like this. So delta T, we're just changing the subject of the formula, is equal to E over MC, which is equal to, what is my energy? I'm given there. 46,000 what? 200. Divided by, yes, your question?
I didn't understand, sir. I didn't understand.
Where exactly?
The first part will be over MC.
This is not physics now. This is simple mathematics here. Let's go back to this. This is simple mathematics. Physics makes an assumption that you are very good or you understand basic maths here. Delta T. What we want to find, the question is asking about temperature here. We want to make T, this simply means temperature change. We want to make temperature change the subject of the formula. What is the subject of the formula here is E. E is equal to. So we want to have eventually T is equal to something. So because we want this to remain only on this side, I divide by MC. Because I don't want MC this side, I divide by MC. M cancels out, C cancels out, simple message. So now I have delta T is equal to E divided by MC. So one aspect of physics, to be good in physics, is to know how to change subjects of the formula. If you are given any formula, you should be able to play around with formulas. Clear? For example, okay, before we look at this, if I have, for example, I'll give you an example here. If I have P power is equal to VI. If I want to make I the subject of the formula, what will be the formula here? If you're looking at this. Tell me so that we are together. What will be the formula to make current the subject of the formula then? I divide, I don't want V here, I divide both sides by V.
It's
So it's
I.
simply P over,
I is equal to V.
yes, I is equal to P over V, power divided by voltage. Because I'm doing the same both sides like this. So that's the same concept we are doing here. We are making T the subject of the formula. Because we are dealing with the question is saying find the initial temperature. Is that clear? There. Making sense? Is it making sense now? You're asking me. You now get the first part, huh?
Confirm the M stands for mass.
M is for mass. I explained. Did
What
you
was the
join the
mass?
lesson?
What was,
You joined the mass
Yes.
in kgs, with the mass in kgs. I think you joined the
what
lesson
was
late.
the mass?
The mass
The
is
mass
there.
there was the
There.
is 5 or 5
Yes,
kg.
M is the mass in
Okay.
kg, E is the energy in joules, C is the specific heat capacity. I think
Heat
you joined
capacity.
you joined the lesson late there. That's why you are
Yeah.
struggling to get this clear. Are we together there? So now look at this now, everyone. Delta T, I understand it's good to ask questions. Now E is what? 46,200 divided by, what is my maximum factor of 5? Mass has to be in kgs, huh? Otherwise if it was in grams, divided by 1,000. Multiplied by what is the specific capacity? We are given 3 what? 385. What do you get? Use your calculators. I think that's where we get her answer, which is 24. But it's temperature change. If you read the question, I'm actually increasing the temperature. So the final answer is T is equal to 20 degrees plus 24 degrees, the temperature change, degrees Celsius here. We get 44. You see that, Natalie? 44 degrees
Yes, sir.
Celsius is my final temperature. Because when I use delta T, it's simply temperature change. It's the temperature that changed because we are adding energy, so the temperature will increase. So this is the temperature change from 20, it increased from 20 by 24 degrees. So we are adding that. Mufaro, is that clear?
Yes, sir.
Okay. Okay. Good question. Huh? These are very good questions that I'm giving you here. Now let's look at another question. How much? So question 3. Oh, Natalia is in the lesson. Chieza, I don't know what's happening with you today. How much energy? How much energy is needed, write the question down, to melt 150 degrees, 150 grams of ice at 0 degrees, at 0 degrees Celsius. To melt ice at 0 degrees Celsius to water, or to liquid at same temperature. Then in brackets, specific latent heat of fusion. Of water is equal to 334 kilojoules per kg. Okay. Now, Reese, are you there? I need to explain something here before we do some calculations. Are you still there, Reese?
Yes.
Okay. Everyone there, I need, so you can write NB before looking at this solution here. Things that you always need to remember. So if we are calculating the latent heat of fusion or vaporization, we ignore the temperature. Because the temperature is constant, we ignore temperature because it is constant. Clear? So what will happen to our formula? Our formula is simply E is equal to MC. Clear? We dropped the delta T there. There is no increase in temperature at that. Clear? Our temperature is simply E is equal to, when we are dealing with latent heat, this question is talking of latent heat of fusion. Clear? We dropped, because at that I showed you from the cooling curve and from the heating curve, the temperature is what? Is constant. Clear? Making sense? Does that make sense?
Yes, sir.
Then the next thing that I want to show you before we even calculate, which is an easy calculation anyway, is I want to compare something here. What did I say was the specific heat capacity of water? Who remembers? I said it was 4,200 joules.
200.
Now, what's the fusion for water? When water is changing from ice to liquid, we are given what? 3. Look at this. This is kilojoules. So it's 1,000 like this. So this is what you just need to raise 1 kg of water, by 1 degree all the time. You require this energy. But now to change water, to change 1 kg of water of ice to liquid, we require this. Can you see how many times is that? Can you divide 3 so that you see how much energy is that? That's a big number there. So if you divide that by 42,000, I think 4,200, can you see that is more than 80 times? Huh? We require so much energy to overcome the forces of rise now You see now, we don't need this calculation, I'm just showing you. You require so much energy to overcome the forces of attraction than simply raising liquid water temperature, than simply raising the liquid water temperature. Clear? All together. We require so much energy to overcome the forces of attraction. Okay, I was just showing you this, but it has nothing to do with what we want. So now let's do solution quickly. We said we dropped the theta, so E is equal to mc. What is the question asking? Energy. And E is the subject of the formula. So what is the mass? Can you see the problem with the mass? What did I say mass should be in? Who remembers? Mufaro? Mass should be in kgs. This is not kgs. So what do we do? 150 divided by 1000. Because 1000 grams gives you 1 kg. Multiply by the specific heat capacity, sorry, the heat, latent heat of fusion, which is 334. Another thing is in kilo joules. We require it to be in what? In joules. So like this. Makes sense now? Be careful now when you're dealing with physics here. Clear? Specific heat capacity should be in joules per kg per degree Celsius. And what do you get? Answer?
$50,100.
50,100 joules. Okay. Question 4. Then we look at some theory, things that you know, adding to things, radiation, convection, and all that. Now, question 4, the last one on this part. Let's write that down, race there, and friends. How much water? So I'm not going to write it down. I'll simply give you 2 minutes to do the calculation. How much water at 100 degrees? How much water at 100 degrees? How much water at 100 degrees? Everyone here writing down the question? How much water at 100 degrees would be turned into steam? Would be turned into steam at the same temperature? Would be turned into steam at the same temperature by 678 kilojoules, kJ, kilojoules of energy, would be turned into steam at the same temperature by 678 kilojoules of energy. It's like kJ in caps, kilojoules of energy. Clear? In brackets, specific latent heat of vaporization, specific latent heat of vaporization of water, is specific latent heat of vaporization of water is 2,260 kilojoules per kg. Kilojoules, not joules. 2,260 kilojoules per kg. Kilojoules per kg. Kilojoules per kg. How much water? 800 degrees would be turned into steam at the same temperature by 678 kilojoules of energy. In brackets, we said specific latent heat of vaporization of water. Did everyone get the question? Is 2,260 kilojoules per kg. Did everyone get every part of the question? Mufaro?
Okay.
Yeah, so did. Is Mufaro in the lesson?
Yes, I'm here.
You got the question, huh? Is there anything that you didn't get on the question? Reese, you managed to copy everything? Krishano, you managed to copy everything?
Yes, sir.
Okay, let's calculate. 2 minutes. Let's calculate. Sorry, let's go back to the question. So when the question says how much water, in brackets, right, they want the mass, huh? We want the mass of the water. It's an assumption here. It's not, in physics, they have to be clear by how much water they're talking about. So they want the mass. How much mass of water? So when I said how much, you can say in brackets or the mass. You need you to calculate the mass of the water. Clear? Now it's clear. You can't complain. Someone is having terrible network issues. To understand what happens. Natalie is you. Can you? Not sorry, Chiedza, can you hear us? Oh, I think we lost him. Unless he's muted or something. Network. Are you guys done? Still working? Okay, everyone should be done then. If we are not done, it means somehow, maybe you are forgetting one or two things. Mufara, are you done? Mufara? Mufara, are you there? What's happening to you with you today? You're always the first to finish. Mufara, are you there? Mufara? Oh, can you hear me? Cristiano, can you hear me? You guys
Yes,
can hear
sir.
me, you're quiet. So what's your answers? What did you get?
So I'm still working out, sir.
Oop. You're doing wrong things. Huh? That question should never take time, if I am correct. It
I'm
means
not
yes.
sure of my answer, but
Yeah,
I got
yeah.
0.3.
0.3 means you made a mistake somewhere.
Yes.
You are very close to correct, but your answer is not correct. I'll show you why. So now, remember, what formula are we using? So what formula are we using? Are we using E is equal to, that's where you struggle now, if you didn't get what we said. Are we using this formula here, or we are using this formula? Mufaro, which formula are we using? Are we using this formula or that formula? Natalia, which formula are we using here?
The second one.
The second one, I explained that. Check your notes what I said. I said when we are dealing with latent heat or fusion, we ignore the temperature because the temperature is the same. So we are not dealing with temperature here. We are simply dealing with E is equal to MC. And can everyone make M the subject of the formula here? We divide both sides by C, like this. Cancel. Sorry, by C, both sides. Cancel, cancel. So it means E is equal, M is equal to E over C. That's how easy that is. M is equal to E over C. Making sense now? E is equal to that over that. Temperature has nothing to do with the question, huh? Because at that, the temperature is the same. So what is the energy that I gave you? Energy that,
678.
and the energy, yes,
678
the energy should be in joules, huh? We're dealing with kilojoules. Now my pen is not writing it. Oh, what's happening? What happened to my pen? Maybe I moved something. I'm sorry about that. So it means is you are dealing with 678,000. You see? Like what you're saying, 678,000 divided by 2,260 multiplied by 1,000, because your energy has to be in thousands. Maybe she's correct. 678, she might be correct here. I think you're correct. I said you're wrong. I think you're correct. Divided by 2260. Yeah, you're correct. 0.3 grams. She's very correct. That's the answer. 0.3 grams. Mfaro, are you in the lesson?
Yes, I'm now in the lesson. My laptop was glitching.
Okay. Now my pen is refusing to write here. Just need to quickly reinstall the drive. I think I moved something. Thing is, once I it slightly moves, don't know how the tablet works anyway. So those are the simple calculations we know. The rest is simply theory, which we are going to do just now. The rest is easy. It's not a difficult topic. Yeah, if you don't like calculations, then what we're doing is the difficult part. The rest is very, very easy. It's one of the easiest topics. Clear? Yes, hold on, just give me a minute to set this up quickly. And cheers that we've lost here, or she can't even hear us. Oh, she was just active when the lesson started. Then we don't know what's happening. Krishana, are you in the lesson?
Yes, I'm in the lesson.
Very nice. Now we're going to look at kinetic theory. So you can write kinetic theory of matter. Kinetic theory of matter. Kinetic theory of matter. Kinetic theory of matter. Just hold on. Kinetic theory of matter. We discuss it. So Takozo, I think we've lost him network, yeah? But the rest of you, I think you're fine. Sorry about that. I don't know what happened to my pen. So practice changing subjects of the formulas for maths and for physics. It's very helpful. Changing subjects of formulas. It helps a lot. Sorry for that. I don't know what happened, but it's almost done. To fix the recording. Okay. Should be working. Let's test it. So I said kinetic theory. Kinetic theory. You know it, huh? Kinetic theory. So what does kinetic theory talk about? Talks about the movement of matter, the movement of particles. Kinetic theory simply states that all particles that make up matter are constantly in motion. Kinetic particles states that all particles that makes up matter are in constant motion. Clear? We know that with a solid, what can you say about the solid? Particles are, it's vibrating what? Vibrating atoms. Vibrating atoms in fixed positions. Vibrating atoms in fixed positions. Clear? Are we agreeing? Solids vibrating atoms. What can you say about liquids? What can you say about the movement of liquid atoms? Yeah, quiet, huh? What can you say about the kinetic energy of liquids? Mufaro? We said solids, they are vibrating in fixed positions. Huh? They are not moving. They are simply vibrating in fixed positions. What can you comment about the kinetic theory, kinetic energy?
So
Yes. Of
what I
liquids?
can say is they're constantly moving, if I remember properly.
Yeah, I've got
And then they also they
flowing
have like
atoms.
space. Yeah, they have space. They have space to like kind of like go through each other, I guess.
Flowing atoms. Then these ones are moving freely. Moving freely in haphazard. Freely. In all directions. Are we together there? Moving freely in all directions. Are we agreeing? Now, when we are comparing these three, we should be able to compare. We're talking of the arrangement of the particles. We should be able to compare them in terms of the volume. What can you say about the volume of a liquid, the volume of this, and the volume of that? What can you say? And we should be able to talk about compression. So what can you say about solids? Solids have got a fixed what?
Volume.
Fixed volume. That's form 2 stuff. Solids have got a fixed volume. What can you say about this fixed volume? Fixed shape or regular shape. Fixed shape, of course, it's going to be irregular. What can you say about liquids?
They have a fixed volume, but shape can change.
Liquids have got a fixed volume. Shape, they fit the shape of the shape. It fits the shape of the container. You know, whatever they are together. They simply take the shape of the container. Liquids and gases. Shape and volume. What's your comment, Reese? You have been quiet. For gas, what can you say about the shape and the volume?
It has no fixed shape or fixed volume at all.
Okay. No fixed volume, no fixed shape at all. That's fine. Okay. Clear? Compression, that's the last thing. What can you say about compression? Can a solid be compressed? Can a solid be compressed?
No.
A solid, you can write it, cannot be compressed. What about a liquid?
No, I can't.
Do you agree with him? When you have spaces here,
No.
like this, so you
So
can compress it, but it's difficult, hard to compress. It can be compressed, hard to what?
Oh,
To compress.
right.
Yes, because when you compress and you're trying to close this gap, it can be compressed, but hard to what? To compress. This one is very easy to compress. Huh? Clear? Very easy to compress. Is that making sense? Or not making sense? Making
Making
sense
sense.
now. Let's look at temperature. Temperature. What is temperature in general? In physics, what do you think will be the definition of temperature? Temperature is the measurement of the average kinetic energy of particles in an object. So temperature is the measurement of average kinetic energy of particles. Average kinetic energy of particles. Clear? In an object. This is what we call temperature. Making sense? What do you use to measure temperature? Everyone knows. We use a what? A thermometer. Clear? We use a thermometer. Clear? Are we together? The guys are quiet. Temperature. So if we were to compare temperature and heat, remember I said heat is the amount of energy translated from a hot object to a cold object. Huh? And we are now saying temperature is the measure of how hot or cold something is. Can you see the difference between temperature and heat? Heat is the energy that we require, or the energy that is transferred from a hot object to a what? To a cold substance, to a cold object. Huh? But we're saying temperature is the measure of how hot or cold something is. I'm making sense? Or not yet? Now let's look at expansion and contraction of matter. Expansion and contraction of matter. I think I'll give you some notes here of matter. Expansion and contraction of matter. Expansion and contraction. When does expansion takes place? When we heat matter. Clear? When we heat matter. When we heat solids, liquids, and gases, the volumes increase. That's what we're talking about expansion. So in general, when we heat matter, when we heat solid, liquids, and gases, the volume increases. Are we together? Why does the volume increase? Who can explain why does the volume increase when we heat up something? Why does the volume increase? Mufaro? Why would the volume increase? If you heat up something, why would the volume increase?
Because it would expand.
Not really. You are not using the physics terms that you have learned here. What happens when I increase temperature? The particles gain what? That's what I'm expecting from all
Kinetic
physics to
energy.
gain. The number one, the particles gain kinetic energy. When they gain kinetic energy, they move further what? Further apart. So if they move further apart, it's increase in what? in volume, because volume is space occupied by what? By matter. Can you see that, Mufaro? So when you heat up particles, when you heat up matter, they gain kinetic energy. When they gain kinetic energy, they move further apart. So when they move further apart, it means they occupy more space. So that's why volume increases. Clear? Making sense? And that is what we are calling expansion. Yeah? Making sense or not making sense? Contraction is the opposite. So contraction, you're saying when you cool down solids, liquids, and gases, the temperature decreases. Because when you reduce temperature, the kinetic energy decreases and the particles move shorter distance or closer together. Clear? And they move closer together, the volume, we're saying it what? Decreases. Is that making sense? Is that making sense? Or not making sense? Oh, the guys are quiet. They're very quiet. This side there? Are you there? I'm saying, are you there? Yeah,
Am
very
I?
quiet. I'm saying, are you in the lesson?
Yes, I am in the lesson. I'm just
Okay.
observing.
Observing. So we're talking of expansion and contraction. Huh? So where do we apply this? The expansion and contraction in general. Which applications? Do we use this?
Measuring hot temperatures.
No, I'm saying applications. Measuring, no. Remember, I'm talking of applications, life applications, where the concept of expansion and contraction is used, especially for solids. That's what I'm talking about. We can't think of any. Expansion. Expansion. Of liquids. You don't know that. Observing. Okay, let me bring closer to home here. Let's say I've got a boat here, or I've got something that has got an opening there. But now I want to, it's like I want to tie this metal, I want it to fit there. But this is too short there. So what am I going to do so that this can fit? What do I do, Mufaro, so that this can fit into this opening here? Slightly it cannot fit. What are we going to do to this?
We're going to heat it up.
Yes, it's a concept of expansion. We heat it up. When we heat it up, it expands and it further opens up. It increases this opening there so that this can fit. Clear? When it fits, this cools down. When it cools down, now it tries to reduce, then it becomes tight there. Is that making sense? Simple physics. Huh? I'm just showing you one application of where you can apply what we're talking of expansion and contraction. So what I'm going to do, I'm going to send you notes. Notes, huh? So when I send you notes, I want you to read on conduction, convection, and radiation. Next time, next physics lesson, we're just looking at questions. Huh? Conduction, convection, and radiation. Is that making sense? Very nice notes, huh? That maybe you can actually print them and have them in your book. Huh? They are very nice, the notes that I'm sending you. Then we talk about that. Then we talk about design of the thermometer, which is in a syllabus. Things that are important when designing a thermometer will be the next thing. So the convection, radiation, and conduction, I want you to do, because it's easy there, to read on that. So do I have everyone's number there? I think so. This there, I'll start with you before I forget. Then Mufaro, I think I have your number in the email. Then Chieza, Cristiano, Natalie, then Takutsu. What correct? For the evening class. Who else who else did I miss for the evening class? We had 7 of you when you started the lesson. Oh, it was 6. It was only Takutsu whose network was playing up. So Takutsu. So did you receive? I have sent you, Natalie. Reese, did you receive?
Yes,
The
I
notes?
did.
I got it.
Go through those notes. Huh? Most of them are pictures. Don't be intimidated by the number of pages. You'll be quick to go through them. So like I said, the rest is simply theory. It's not difficult. So we need to know the issue of design of thermometers, conduction, convection, radiation, and to answer questions based on that. But we'll look at that in detail in the next lesson. Clear? Makes sense.
Yes,
Yes,
it makes
sir.
sense.
Then what I also encourage you everyone is to have your syllabus for every subject. Don't just depend on your teachers. Now, I'm not saying anything bad about a teacher. I'm saying it's good for you to, like, when you are doing a topic, you go through the syllabus. That's what I'm talking about. When you go through the syllabus, you look at the requirements. It's easier because you can even understand the requirements. What's expected, what you're expected to know, clear for every topic. Make sense?
Yes, it does.
Okay. That's great. So, physics, thermal physics. So when you have done that, what I'm talking about, when you have done your, when is our next physics lesson? Because there's something that I want you to try. When is our next physics lesson? Can you check the timetable that I sent you guys? When is the next physics lesson? Mufaro, what timetable, what does it say?
It was on Sunday, but then we changed it to Tuesday.
To Tuesday. Yeah? So you have lots of time to do this homework. Yeah? So I'm sending you homework here on this topic. It's a multiple choice. Once you have gone through the notes that I've sent, I want you to try the multiple choice, then submit it before Sunday on everyone on thermal physics. And thermal properties. There. I'm sending right now to everyone. So we said before Sunday. Who did I leave besides? I said Cristiano, Natalie. Cristiano, did you receive the notes that I sent now? You received them, huh? Clear. Okay, we are done for today here. So I've sent you that. So I want you to read that. Then try to submit when you've done. Try to answer those questions, huh? And submit before what? Before Sunday.
Sunday.
Then the first thing is we revise, then we go through other things that you need to know. Clear now? It's an easy topic, huh? Mr. Aris. So we'll see you tomorrow for ICT. I think those that do ICT.